Radioactive waste and how to manage it is one of the major concerns surrounding the energy production with nuclear fission. It is classified into low, intermediate, and high-level waste. Low-level waste consists of only slightly radioactively compromised items, like paper or clothing. It makes up the majority of the volume of all nuclear waste, but only 1% of its radioactivity, and because it has such a low radioactivity, it is generally considered safe to handle and transport it without shielding. It only needs to be isolated for a few hundred years and can be disposed of in near-surface repositories. Intermediate-level waste has a higher radioactive contamination, like fuel cladding or other items that came in contact with the fuel. Although it has only a small portion of the total waste volume, with 4%, it possesses noticeably more radioactivity than low-level waste. Therefore, it requires shielding and a high degree of security and containment. Near-surface disposal is only suitable for short-lived forms of the waste. Long-lived waste is usually opted to be disposed in deep geological repositories. High-level waste is either spent fuel or waste from reprocessed fuel. It has only a small share of the total volume, but holds 95% of the waste's total radioactivity. And because of its high radioactivity, it generates significant amounts of heat. This is why it is kept in fuel ponds for at least 5 years, so that it can be cooled by circulating water before it is converted to dry storage, where it is shielded by concrete and cooled by air circulation. Since most of its radioactivity diminishes within the first 50 years, it is worthwhile to keep it retrievable and supervisable for the first few decades. However, keeping the waste in interim storage facilities may make it more vulnerable to attack or to be affected by accidents like plane crashes. According to a B.U.N.D study, there's also the issue of insufficient possibility to repair defective containers. In order to ease the storage and disposal procedures, the waste can be processed to reduce its volume. One of the main approaches is incineration, which is mostly used for low-level waste and results in up to 100 times less volume. The other one is compaction, also mainly used for low-level waste, but for intermediate-level and transuranium waste as well. Depending on the type of waste, this method reduces the volume by a factor of 3 to 10. Additionally, the waste needs to be immobilized. This is done, for example, by cementation, where the low or intermediate level waste in form of sludges or fragmented solids is placed in a container, cement is added and then mixed with the waste. Another method is vitrification, where borosilicate glass is used to stabilize high-level waste. If the waste is liquid, as is the case for reprocessing waste, it is dried to form a powder before it is given into the molten glass. Furthermore, high-level waste can be incorporated into a ceramic called synrock or composite forms of synrock and glass. Synrock is composed of several natural minerals and it forms very robust pellets and results in a significantly smaller volume than the previously mentioned methods. Apart from storage and disposal, transportation of the waste is another area of concern, since inadequate shielding could pose serious health and environmental risks. However, despite roughly 15 million packages being shipped each year, there has yet to be a breach. The requirements for robust nuclear waste containers are quite elaborate as well. They have to withstand a 800 degrees Celsius hot fire for 30 minutes, a drop from 9 meters onto even and firm ground, a 1 meter drop onto a steel spike, and submersion in 15 meter deep water for 8 hours. Although those kind of precautions make a leak highly unlikely, as with almost any hazardous materials, the risk of accidents exceeding security measures will never be zero. So far, final disposal options for high-level waste are not being used anywhere in the world. The World Nuclear Association states that those are not yet necessary, since spent fuel may still be reprocessed, because although reprocessed fuel is not currently competitive compared to new fuel, it nevertheless holds some value. But regardless of being necessary or not, final repositories are not yet ready anyways, and instead in various stages of research and development, depending on the country. This has to do with the demanding challenge of selecting a sufficient site and disposal method. Because although the fission products are drastically decreased in radiotoxicity during the first 500 years, as can be seen in this diagram with logarithmic scale. The decay then stagnates, and the longest lived ones can have a radioactive period of tens of millions of years. Among the long-lived fission products of concern, the most active and short-lived one is technetium-99 with a period of about 215,000 years. This means it is generally regarded necessary to ensure the waste's immobility and shielding for a few 100,000 years. In order to do so, it is best to find stable environments in remote locations, but there is still some indecisiveness on whether the sites should be forgotten or future societies somehow be informed about the dangers of tampering with the site. One of the disposal options proposed is the process of transmutation. This is technically not a disposal option but a processing method. However, if it would be possible to transmute all long-lived nuclides into shorter-lived products, the waste could be harmless after a few hundred years, making long-term disposal obsolete. However, as of today, transmutation only serves to reduce the waste quantities. Isolating the nuclides for transmutation is the biggest challenge. If this isn't done properly, there might be more radioactive waste created than eliminated. Another disposal option might be launching the waste into space, but this is not only costly, there's also the risk of launch failure, making this option not viable. Long-term above-ground storage was also considered. Repurposing current storage facilities means the containment would have to be replaced every 200 years. Alternatively, we could build more permanent above-ground structures, maybe lasting some 10,000 years. But both options rely on future generations to manage or at least supervise the waste, which is why this has been abandoned due to the long-term instability of societies. A disposal option used in the 50s and 60s for low and intermediate level waste was sea disposal. The idea here is to use the ocean's vastness to dilute the waste and its radioactivity, but because of concerns surrounding the exposure of maritime wildlife, it has since been banned worldwide. Deep geological disposal, which puts the waste underground in stable geological environments, is widely favored. It offers advantages such as large distances to live nature, high and long shielding capacity in some soil layers, and offers stability for hundreds of thousands of years, due to the often very slow geological processes. Furthermore, this option does not require future generations to supervise the waste. For smaller waste forms and overall smaller quantity of the waste, deep boreholes might be a good solution, although they would be rather costly for large quantities. Here, a borehole's lower 2 kilometers are used to dispose the waste, and the upper 3 kilometers are filled with sealing material like bentonite clay or concrete. The boreholes can be drilled on or offshore, but subseabed disposal is not permitted as it is a form of sea disposal. A disadvantage of this method is that the waste would not be retrievable. The generally favored method of deep geological disposal is the use of mined repositories. It involves the disposal at a depth of 250 to 1,000 meters. The use of buffer or backfill is optional, and its necessity depends on the environment since some are self-sealing, which means the waste can be retrievable not only short-term, but optionally also long-term. Disposal in clay is being developed in various European countries, with Sweden and Finland being among the closest to implementing the disposal method. Clay is beneficial since it has low permeability, limiting water flow. Alternatively, salt strata are also a somewhat popular choice due to the very little or even absent water flow in salt environments. And a pilot plant in New Mexico is implementing disposal of long-lived intermediate-level waste in salt strata. For the same reason, salt dome formations are considered as well. Germany favored those kind of environments as contenders for final repositories before 2017, but was incited to reconsider when the prototypical project in the former salt mine, Asse 2, ultimately failed. Overall, the final disposal of high-level waste remains a work in progress, and although there are promising methods being developed, many countries still face significant obstacles, like the lack of fitting geological environments or only very small amounts of waste that are to be disposed. To help this, international solutions have been proposed several times, but so far none are being pursued since every country is ultimately responsible for its own waste.